In this video lesson, we are going to describe a simple quark model of hadrons in terms of up, down, and strange quarks and their antiquarks. And then we are also going to discuss the nature of the strong nuclear force, weak nuclear force, and electromagnetic force and gravity. But we're going to only do it in an introductory manner, and we will look at this in more detail in a later video lesson. So let's start off with an introduction to the four basic forces. So we all know about gravity. We also experience the electromagnetic force. We've seen this when magnets attract and repel, and when we see opposite charge attract and like charge repel. And in essence, they are basically different manifestations of the same force. These two forces are forces that we do not come into contact with on a macroscopic level, namely the weak force and the strong force, and they are both nuclear forces. So we will revisit this in more detail, in much more detail later on, as has been mentioned. But a good thing to do is to actually look at the relative strength. So if we take the strongest of the forces, the strong nuclear force, which holds protons and neutrons together in the nucleus, and we assign that a value of 1, then we see that the electromagnetic force is 10 to the minus 2, which is 1/100th the strength of the strong force. And then we see that the weak force is 10 to the minus 13, which is exceptionally small. And then gravity is even smaller, 10 to the minus 38. Now we know that gravity is a significant force in the universe. And the reason for that is that gravity is purely attractive. So that plus sign there is for attractive. The negative sign is for repulsion or repulsive. But we see that gravity is purely attractive. And so when you have a large amount of mass together, like for instance in a planet, or you have it in a star or in a black hole, then all of that adds up. There's no repulsive force in order to cancel out the attractive force. And so then one gets a significant force, like for instance the force of attraction between the Earth and the Sun. The electromagnetic force is attractive and repulsive, as is the weak force and the strong force. Now, when it comes to range, both gravity and the electromagnetic force, they fall off with 1 over the distance squared. So in other words, the force has an infinite range. So both gravity and the electromagnetic force have an infinite range, and they fall off at 1 over the distance squared, which means that the strength of the force is inversely proportional to the distance squared. Whereas with the weak force and the strong force, we see that their ranges are exceptionally small, 10 to the minus 18 meters and 10 to the minus 15 meters. And we'll discuss this later on as to why this is the case. So there are 6 flavors or 6 types of quarks. We have the up, which we represent with the U, and it has its antiparticle, which is U bar. We have the down quark, D, with its antiparticle. We have the strange, the charmed, the bottom, and the top quarks. Now, if we look at their spins, all their spins are a half, and the up and the charmed and the top all have a plus 2/3 of the base charge. That's the charge of the electron, or should I say the magnitude of the charge of the electron, which is 1.6 times 10 to the minus 19 coulombs. And the down and the charmed, the down and the strange and the bottom, they have 1/3. The plus charge is for the particle, and the negative charge, the one at the bottom, the sign at the bottom, is for the antiparticle. So we can see the anti-up quark has a negative 2/3 charge, and the antiparticle for the charmed quark will be a negative 2/3. We see, for instance, with the strange quark, it has a negative 1/3 of the base charge, or the elementary charge of an electron, and its antiparticle, the S bar, is plus 1/3 of the base charge. Their masses are measured in gigaelectron volts per c squared, and we can see that they vary considerably. We can see that the top quark and the bottom quark are huge in mass in consideration or in comparison to the up and the down quark. So we've mentioned antiparticles, so let's formally discuss them. So an antiparticle is a subatomic particle having the same mass as its ordinary matter particle partner, but has the opposite electric charge and opposite magnetic moment. So we're not really going to work with the magnetic moment, it's related to the spin, but we find that, for instance, the electron has a charge of negative 1.602176565 times 10 to the negative 19 coulombs, and the positron, which is this antiparticle, has got the same charge, magnitude of charge, but opposite sign. We see that their spins are the same and their masses are the same. So it's the charge that is the difference. What is a hadron? Well, a hadron is a composite particle made up of two or more quarks held together by the strong force or the strong interaction. We sometimes refer to it as the strong nuclear force or the strong nuclear interaction as well. There are two broad classes or families, namely the baryons, which consist of 3 quarks, and the mesons, which consist of 2 quarks. So the baryons can be represented as 3 quarks that are attracted to each other by the strong nuclear force, and the quarks carry color charge, as we have discussed, and there's something called color confinement, which we've also discussed, but we haven't called it that, and that basically says that all hadrons must have 0 total color charge. We also refer to this quantum number as the color charge, which means that each of the 3 quarks must consist of the 3 colors, red, blue, green, which equals white, or a 0 color charge. Now, once again, I want to stipulate that the quarks don't actually have charge, but they have this quantum property, which we model using charge. Later on in this module, where we are discussing nuclear structure and discussing nuclear processes, we are going to be using the baryon number, or as some people say, the baryon number, more extensively. But for the time being, the baryon number, the symbol B is used. So for a proton, its baryon number is 1, and it consists of 2 up and 1 down quark, as we know. And for the neutron, its baryon number is also 1, and it consists of 1 up quark and 2 down quarks, which implies that each quark has a baryon number of plus a third. Now, with antibaryons, we have that the antiproton, which consists of anti-up, two anti-ups, 1 anti-down, has a baryon number of -1. And for the antineutron, it has a baryon number of -1. So therefore, each antiquark has a baryon number of -1/3. Now, there are many baryons, and we are only going to look at a few of them in more detail. So if we look at this table, and you don't need to learn all of what is in this table, we have the category, the baryons, we have the name, so we're looking at the proton, the neutron, the lambda, the sigma, the chi, and the omega, the particles, the antiparticles, and the rest mass. Now, the rest mass is when they are stationary and they haven't got a relativistic energy because of their of a high velocity. This B here is the baryon number, and we'll talk about that in more detail a little later. And then the lifetime is in seconds, and we can see some of them are very stable, like the proton and the neutron, but some of them are hardly exist. They have lifetimes of 10 to the minus 20 seconds, 10 to the minus 10 seconds, so they are almost non-existent. So let's go and look in more detail We look at the protons and the neutrons. We've worked with them already, and the antiproton and the antineutron. We've got their rest masses, mega electron volts over c squared. And so we see here that if we look at each of these, there are either 3 quarks or 3 antiquarks. So that's what makes it a baryon. Now, ones that are unusual that we haven't come across are, for instance, the lambda 0 and the anti-lambda 0. And we can see that here you've got UDS, an up, a down, and a strange quark, and the anti-lambda 0 has got the antiquarks, but the same composition, but of antiquarks. That's why it's an antiparticle. Then we have the sigma particles, sigma plus, sigma 0, sigma negative, and the antiparticles, which sit here. And once again, we can see that they are going to have opposite sign. We then have the chi particles, and likewise they have, it's exactly the same. The chi particle, chi 0, up, 2 strange. The antiparticle, the anti-chi 0 is anti-up quark and 2 anti-strange quarks. And then we have the omega baryon, and here too we see once again that the antiparticle has opposite charge, and also the quarks are antiquarks. So these are the baryons that we will deal with in this course. When it comes to the baryon numbers, we can see they're all 1 because they're all baryons, but we see the top sign here is for the particle, and the sign at the bottom, the negative, is for the antiparticle. And in the exercises that we give, if we are working with a strange baryon, something that's not a proton or a neutron, then we will give you the composition, and then maybe ask you to work out the charge. And when it comes to reactions, we might ask you to work with the baryon numbers. But for the time being, it's important that not that you learn all of these, but that you can see that there are many different baryons and antibaryons, and they all consist of 3 quarks, albeit varied, up, down, strange. So let's look at the mesons, or as some people would say, mesons. So it's a bit like tomato or tomato. However you prefer to say it is fine. So if we look at the mesons have got consist of a quark and an antiquark, and so their total color charge must also be 0 or white, and so the quark will either be red and the antiquark anti-red, blue or anti-blue, green or anti-green. We've shown before how it all adds up to white. The baryon number for mesons is 0, and which is different to mesons, because albeit that mesons are hadrons, they're not baryons, so it makes sense that they're 0. And so we can prove this because a meson consists of a quark and an antiquark. We know that the total baryon number will be the sum of the baryon numbers of the quark and the antiquark, which will be plus 1/3 and plus negative 1/3. Remember, the antiquarks have got negative 1/3 baryon number, and that adds up to 0. So that's basically saying that mesons are not baryons. So now when we look at the table here of mesons, we see that we've got pions, kaons, and eta mesons. Okay, that's the Greek letter eta, that's the Greek letter kappa, and that's the Greek letter pi. So pions, which are pi mesons, kaons, which are kappa mesons, and you've got eta mesons. Now, if we look in more detail here, we see that the pi plus pion consists of an up and a anti-down quark. And the pi negative, which is the antiparticle, is exactly the opposite. It consists of a anti-up quark and a down quark. So it's exactly the mirror image of that. The pi zero, this is where it gets way more complicated and goes way beyond the scope of this course, is you get mixtures of the up anti-up and the down anti-down. We're not going to try and explain it. It's got to do with the nature of the solutions that come out of the quantum mechanics surrounding this. But we see here that in actual fact, this doesn't have an antiparticle. It is its own antiparticle, and the same is true of the eta zero. So with the kaon plus, it's up and an anti-strange, and for the kaon negative, which is the anti-particle, so it should have an opposite sign to the K plus, which it does, it's a anti-up and a strange. We also have the K0 and its antiparticle. So here too we see their rest masses are in the mega electron volts per c squared. Their baryon numbers are all 0, as we've mentioned, and they have extremely small lifetimes. Much less than a second. So here too, it's important to know that there are many mesons, but these are the ones that we are going to focus on and the ones that you need to know. So by way of an example, if we look at the pi plus meson, or the pion, then if we do a representative diagram, it consists of an up and a down quark, and we can see that they've also got opposite spins, plus a half, minus a half, and they are, the color charge is red and anti-red in this case. And so we're going to see here that what we get is that the total spin is 0, which makes pi mesons actually bosons, whereas we see with the baryons, they have half integral spins, which makes them fermions. We'll discuss this in more detail later on. We see here that the total charge here is plus 2/3 plus a third, and because normally a down quark has got a negative a third charge, but because it's the anti-quark, it's going to be the opposite sign, so it's plus a third, and that makes it plus 1. Let's once again, that plus 1 means it's equal to the magnitude of the elementary charge or the base charge, namely 1.602 times 10 to the minus 19 coulombs. So you will receive exercises and practice that involve problems like this.